All right, KNES 415 biomechanics. This week we are going to patiently and simplicity, we're going to keep it simple, look at some tools that we can use in the area of biomechanics to measure some of the things we've been talking about all semester. Well, what are some of the things we've been talking about all semester? Muscles, muscle function, specific muscles. In addition, when we had the more physics stuff, we were talking about forces and you know vectors and magnitudes, and so in a biomechanics lab, right, a science-based place where you could play with these numbers. How do you get the numbers? How do you get the tools to play with? Where do you get them? Do you make them up? And no, we could do hypothetical stuff, but the answer is that we measure them, and then we can use some equations to answer more things or to interpret data. But you got to have data to be able to play. And so that's what we're going to talk about today. Some of the different ways we can get data, and some of the different ways we can look at that data. And one of the biggest, I say biggest, is the most fun is electromyography in a biomechanics lab. And I say fun because EMG, electromyography, tells you when muscles are doing a job. Now, I taught you basically how to figure out this stuff, right? External force doing muscles doing a job. But this can kind of confirm what you think. Not everyone's going to have electromyography laying around, so we still have to use logic to figure out if things are working. This could tell you how much it's working. This could tell you if it's overworking. This could tell you if muscles have fatigue. It's kind of cool. A neat fact, we'll get into it later, but actually electrical activity goes up when a muscle is getting tired, because it makes sense. If the muscle is getting tired, it's trying to recruit everything it can to hold on for dear life, and so the electrical activity goes up and up and up. So just to give you a heads up, I will be turning around a lot because me looking at the camera, I see flippy flip. So I want to make sure that I'm getting the key points. Remember, this is just an introduction to some of the methodology that we use in biomechanics to extract data, to get stuff, useful information. This isn't just in biomechanics labs. Places have electromyography in clinics and hospitals. So a lot of you may be using this stuff down the road, and I wanted to introduce you to it in biomechanics research or clinical. Okay. So the definition of electromyography: detection and recording of the electrical signal produced by muscle tissue as it contracts, working above resting tone. Now, a couple things off the top of my head. You were most likely familiar with this concept. EKG, right? Where you put the electrodes and you see the electrical activity of the heart. Any movie or TV show you've seen people do EKG, electrocardiography. Well, it's the same concept, but instead of recording heart muscle, cardiac muscle electrical signal, here you're taking electrodes and you're recording surface muscles. Why surface muscles? Because deep muscles like the soleus or the brachialis, it's too deep for the surface electrodes. Surface electrodes just means that these electrodes, these sensors, fit over the top of your skin. So the sensors will really only work for top-lying muscles. Because the top-lying muscles, not only can we sense those better, their electrical activity, but they would cloud any signal that we're trying to get below them anyway. So surface electromyography is great at looking at what's working close to the skin. There are ways to get electrical activity of muscles that are deep. but they require wires. They call them inner-dwelling electrodes, where you put them into the skin. Like think about like a needle, needle inner-dwelling electrodes, and you could put it in and go into the deep and measure electrical activity up in there, up in there. So they have ways to get EMG on deep muscles. Okay, let's see. Okay, so think of it like this. If anybody's ever worked in a clinic and you put a stim machine on you, where you crank up the electrical activity of the external electricity, and what happens to your muscle? Your muscle responds by contracting more and more and more, meaning that the more juice you give it, the more your muscle contracts. They're directly proportional, right? You increase the voltage and your muscle responds by working more. So this is a reverse of that. I mean, it's the same concept, but it's a reverse of that. With electromyography, the more your muscle voluntarily contracts, right? If I say, hey, Brian, contract the bicep more and more and more and more and more and more, the electrodes are going to measure more electrical activity from the muscle itself. Okay, so they're directly proportional. The more juice you give the muscle, the more the signal is going to ramp up to correlate with contraction amount. Okay. So that's basically it. Don't get caught up with cells, membrane potentials. That's all grad school stuff. Basically, you're just measuring the electrical signal. Now, of course, that signal is very tiny, but that's why you have this expensive equipment. It can measure these little tiny signals and then ramp it up and amplify it into signals that you can actually see, treat, process, and you could do some cool stuff with it in graduate school. Okay. Okay. So again, I kind of hit on this earlier. Why would you want to measure, and S is for surface electromyography? Man, you can with clients, you can put these surface EMGs on and check to see if muscles are turning on when they should turn on. In biomechanics, timing was a big issue with us. When we would at Auburn in our lab, we would want to know not just if a muscle turns on, but when that muscle turns on. Is it turning on time? Is it not only doing a job, but is it doing a job in the sequence that it's supposed to be doing a job? Other things you can look at is latency. How much time did it take when you said, hey, muscle, do something, and then the actual mechanic, they call that electrical mechanical delay, but you can look at a lot of different things, okay? If it's active, is it working? Post-surgery, right? That's some interesting stuff to look at. How is the muscle reacting naturally or not naturally to reinnervating itself? Okay. Now, EMG does not tell us necessarily muscle strength. What that means is that in certain instances, we kind of control for a few things, but it tells us as the electricity goes up, the muscle's effort goes up. But what it means by the strength of the muscle is that because of all different kind of factors like your water level, how dirty your skin is, that's why we try to treat it. We try to clean and debris the dead skin cells. But different people have different conduction of their skin. So what we can't say is that if I put surface EMG on my bicep and you put surface EMG on your bicep and you recorded higher electrical activity, you know, in terms of like millivolts, your millivolts was greater than my millivolts, then your muscle is stronger than my muscle. That's not how this works. Okay. Does that make sense? There's just so many different factors. We can't say your millivolt more than my millivolt, therefore you're stronger than me. Okay. All right. Okay, let's take a look at it. So, electromyography, the detection, amplification, recording, processing, and analysis and interpretation. 3 ways of recording the signal. We have the surface electromyography is the most popular. Again, we call it invasiveness. It's less invasive. You don't have to put needle. I mean, all right, we're going to put some needles in you and check. I mean, that could be warranted, but it's just a heck of a lot easier to just slap electrodes and go, right? That's again EKG. Just slap electrodes, see electrical interpretation of the heart as electrical signaling processing. Okay, all right. So we detect signal, we amplify it, we record it, we process it, and then we interpret it. Sounds like a nice research equation there. Okay. So for this, the main thing that I'd like for you guys to know is the type, right? Surface electromyography is the most common used because it's the less invasive. It's easy, it's quick, and it's not risque. Okay. So this is an example of how to measure EMG, position the patient, determine the electrode location. Obviously, positioning of the patient depends on why you're using EMG. Determining the electrode location, they have books that give like location maps. Like for instance, one study I did where I was looking at a certain muscle in the forearm, you had to use your fingers and you went 1/4 inch away and then you put your middle finger in between these bony landmarks and then that's roughly, but that just kind of gets you in the area. What really kind of found that motor unit was we had a little stem gun. It's really cool. It was like a little handgun, and when you pulled the trigger, it would shoot little stem pulses. Nothing crazy, just a little bit. And so what we do is we would use the literature to find roughly the area of the motor unit, basically the place of the muscle where the signal easiest comes to the surface. And we take that little stem gun, and when you hit the area that was most sensitive to reading that, then the muscle would twitch, right? And you'd be like, hey, I found the spot. And then you'd place your electrodes accordingly based on the kind of system you have. Okay. Now this is what I was talking about earlier about skin prep. Because these electrodes fit on the skin, you have things like dead skin cells, dirt, oil, that could get in the way of the signal going from the motor unit to the outside of the skin. So again, trying to keep this as simple as possible. Skin prep, you want to shave the area that you're about to test by the motor unit, by the muscle. Why? Hair can get in the way also. Hair is inert. It's not going to transfer any electricity. You got to get it away. So you got to shave the area, then debride the area so that we take some small little patches of sandpaper and debride, and that's just to get dead skin cells out of there. Okay, so the skin nice and smooth, and the sensors are better able to sense that electrical signal. Okay. Now again, this is me introducing you to this. Place and fix the electrode securely. Y'all, there's a lot of different types of systems. These are duals. You usually have a positive, a negative, and then a ground. Sometimes the ground is in one of the electrodes. And basically the reason you have 2 of them is because it's like a race. And when the electrical signal passes through, it kind of gets sensed by the first sensor and then the second sensor. And well, how much time did it take to go from the first? And so having 2 there kind of helps to measure changes and differences as the signal propagates. Okay. So again, this is just an example of one system. I've used systems where these were split, and you had to put them on. And then I've had systems that had 3 wires. You had a positive, a negative, and then you had a ground, and you had to put the ground on a bone, or make sure you put it on an inert, like, piece of tendon. Okay, I'm just getting to some importances. So when you're measuring, so like say here the person is seated, flexed, and the clinician puts force in a direction of plantar flexion, because we want to measure dorsiflexor muscle up here, okay, tibialis anterior probably. And you say, okay, push against my hand. Now, what the signal is going to say is that, remember how we talk about at rest, resting tone? So look, there's still stuff happening. But once you start to work above rest, and all of a sudden you're going to go, whoa. You're just going to get a bunch of ups and downs, and that's because you're going to have some positive signal, some negative signal. Just think EKG, right? It's just a bunch of EKGs that are just compressed together, because unlike the heart that has to have latency to function, here you're silly or right? So it's like a ton of EKG signal just compressed because there's no latency. And it's what we call raw EMG. That's just signal. And raw EMG is fun because it just tells you that a muscle's working above rest. Now we have to process this data. We have to do some stuff to it. And again, I'm not going to hold you accountable for that. We're just delving into some cool things. I'll tell you what's important to learn or to have on your test. So again, not active. Now, not active above rest, right? Those muscles are still active, but that would be resting tone. So hopefully a lot of this is coming full circle from 310 and 415, right? And then all of a sudden, you tell that muscle, that surface skeletal muscle, that superficial skeletal muscle, to do a job, and you're seeing ultimately what makes the muscle respond to work more, and that's electricity, electrical signal. You have to tell it, you have to call it and say, hey, we need you to do this job, and we need you to do the job with this much effort. So if you increase the effort, you'd increase the squigglies. And if you decrease the effort, you decrease the squigglies, and if you had rest, you'd have little bitty squigglies. It's cool. Okay. Rectified EMG, super duper simple. It's basically just an absolute value. Because the signals go above and below 0, it's just natural with latency, right? Remember how, depolarization, repolarization. So if you averaged above and below, they would cancel out, you'd get nothing. So we rectify it basically to take an absolute value to just look at one side of the 0 sign, like all the positive. Okay, so that's what that means. Timing, that's what I was talking about with latency period, right? Where you can see things in EMG, like where the first signal hits. You see that little onset? That's where the first signal hits, and then you can actually see when the muscle turns on, when the muscle turns off. Rectified, okay, smooth. So smoothing data basically just takes these really big, steep, looks like a city, and just makes it more into a visible trend line. So almost just kind of shrinks it down into some so what, where you can actually look at trend lines. Smooth and rectified. Okay. Filtering the data actually helps us see it a lot easier as well. Filtering just means like it's electricity. So we have electricity coming from ambient light, like the light produces electricity that or signal that the sensors might pick up on, and other muscles and other electricity it might pick up on. So filtering process basically, you can tell the equipment, hey, eliminate any electricity at these frequencies that are common for lighting or common for other areas, and so basically the system says any voltage at these different frequencies we're going to extract out, because we know that's not the muscle. So that's what filtering the data means. There's fatigue, okay? So again, I'm not going to go into this in super high detail, but you can look at fatigue with electromyography. That's all you got to know, is that you can look at how a muscle is, you can tell if a muscle is fatigued based on the trends of electromyographic data. Okay. So I'm going to emphasize the key points on this slide. Factors that affect surface EMG signal: impedance of the tissue, impedance, things that get in the way. That's all that means. Hair, dead skin, oil. That's why we prep the area, okay? And it's also important to be consistent in your prep. That's why, like when we would do EMG studies at Auburn, we would try to have as much consistency as we can, even that if that's having the same person do the process of debriding, and because just it lessens the error. If the same person did that same subject over and over and over again, then it would have a greater chance of being more consistent. Okay. Crosstalk between muscles. That means that if you put surface EMG in an area that has multiple muscles, you may get crosstalk. You may have one muscle doing a job also whose signal might bleed over or diffuse over, and then all of a sudden that muscle that you're measuring is getting credit for its work and someone else's work. Okay. Changes in geometry between muscles and electrodes. That's when in our lab we tried to do all of our electromyography in isometric situations. Why? Because when you have no change in length when the muscle is working above rest, then there's no changes in the geometry. Everything stays the same. When you start moving, not only do you have movement in the skin, but you actually literally have movement in the muscle length. And so a motor unit that you are measuring here might shift. It might go over here. It might go over here. There may be changes in the geometry between what you're measuring and what's being measured. Okay. And then again, external noise, just things that generate shaking. The wires cause noise. So trying your best to create an environment that's as static as possible. It's not that you can't do non-static stuff, but just to really get as a real accurate measure of what's happening, you want to have your conditions as fixed as possible. Okay. The 3 P's: position, prep, and placement. Consistency. Okay. I'm just glancing over for important stuff, okay? So the key thing here is electromyography by itself, in terms of looking at what can you measure from it. You can measure if muscles are on. You can measure latency, how long it takes them to come on. You can do what we call percent MVC, maximum volitionary contractions, where you could say, well, okay, contract your bicep as much as possible, go, 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 and this is your max level. And then you can look at sub-max things and make it as a percent of your max. But in all of those cases, it's isometric. Again, fix things, fix things, fix things. Let's see. All right. So that was a quick, let's see, try to find some more pictures of some integrated electromyography of the bicep right there. Let me see if I could find another picture. Ooh, some process data. That's always fun. Ooh, there we go. Here's a needle. Here's a needle electro EMG. Okay, I wanted to try to find you guys. So what they're doing here again is instead of doing surface electrodes, they're actually putting a needle in there to measure the electrical activity. That's when you can get into deeper muscles. Also, needle EMG, you don't have to deal with some of the same issues of surface. Like you don't have to deal with skin, you don't have to deal with hair. You get right to the source. So, most everything is trade-offs. When we get into the Wednesday lecture, I'm going to talk a little bit about motion capture and force plates, and it's about trade-offs. There's no perfect. It's do you want uh, the accessibility, the ease, there's hardly any risk with surface electromyography, knowing that there's other factors that might get in the way of what you're measuring. Or for some clinics, you need to get in there and get more accurate data, specifically where the rubber meets the road, as some people say, and you don't have to worry about all of the other factors of the surface EMG. One negative is you're being intrusive. You're sticking a needle into someone. You better be certified or are cleared for that kind of electromyography. Okay. So the key thing in wrapping up here is I wanted to check out that needle electrode, man. That looks so cool. I just wanted to introduce you guys to electromyography. I wanted to introduce you guys to the fact that it's just like EKG. It really is. It's just that instead of heart measurements, we're doing muscle measurements. And unlike the heart, which is involuntary, right? You can exercise to make your heart work harder, but I can't just think it like I can a bicep, right? I could take my bicep and make it work more, make it work less. So it makes sense that when you're looking at EKG electroactivity, there's going to be a lot of consistency there. Again, unless you're being stressed. But with muscles, you can, okay, hold a 10-pound plate. Okay, this is at rest. Put the 10-pound in your hand. Okay, hold a 20-pound weight. Okay, hold a 30-pound weight. Hold a 40-pound weight. You see what I'm trying to get to? So there's a lot of variability there that we can look at. For most clinicians that looking at EMG, is the muscle doing a job? Is it actually doing a job? Remember, we have a lot of different muscles that help pull in certain directions of motion. So sometimes we need to see, hey, is this muscle on? Maybe there's a reason. Maybe there's some palsy there. Maybe there's a nerve problem. That muscle is not getting the innervation that it should. We need to check. It's almost like if you think of each skeletal muscle as being alive, like a heart, you check someone's pulse to see if they're alive. This is almost kind of like checking, or one way to use electromyography is checking the pulse of individual skeletal muscles to see if they're alive, to see if they're or being innervated. And if they're not being turned on, then they're going to atrophy. And that may cause problems, may cause contractures, may cause other muscles to have to compensate. So there's a lot of different reasons why we just need to check the pulse of different muscles in the body, especially if someone's having some problems. So that's one thing we can do or a big thing in clinics to check electromyography is just to see if those muscles are alive, just to see if they're getting innervation. In biomechanics, in research, electromyography is super duper fun for a lot of different things. Looking at uh, different exercises and does this muscle work more or less when you do certain things. In my research, I looked at people that had chronic tennis elbow, and I looked at that muscle and I put different loads in the hand, and sometimes I would put loads or the same load, and sometimes I would give like wrist torques, where these muscles were not only working to stabilize the wrist because the finger flexors are trying to flex them, and so those wrist extensors had to turn on to neutralize the wrist. But what would happen with the different muscles in that group when you would supply other forces, other factors? Did they stay the same, or did one compensate for the other because one's getting inhibited with the finger flexor? It's boring. But the point is that those are a lot of things you can look at. The relative contribution. When you're doing certain exercise, certain tasks, or certain treatments. What happens when you give someone a certain treatment? Does the muscle change its contribution? Does it work more? Does it work less? Does it shut off? Does it wake up? So a lot of different cool things. So in summary, you need to know what EMG stands for. You need to know that EMG is trying to measure, it's a kinetic means of measurement, forces. We're looking at muscle pull, contraction, influence magnitude, basically. And it's not that, again, it's not that the electrical signal correlates to the work, because again, all these factors I talked about earlier, but there are certain conditions that you can do where your electrical activity as a percent of your max can correlate to muscle force. So there are certain conditions you could do where that can be correlated. Why would you use EMG? Clinicians, it's mostly to see if muscles are alive, if they're being innervated, if they're getting signal. You're trying to look in to see if these muscles are if all the plumbing checks out. It's like running a test on the muscle and seeing if it's getting what is this. So in clinics, that's what it's used a lot for. Don't get EMG confused with STEM treatments. STEM is the machine is giving the electricity. EMG is the machine is measuring your electricity. Okay. All right. So electromyography, this is found in most biomechanics labs, and it's a fun way to measure muscle work. Okay. All right, guys. On Wednesday, we're going to do force plates and motion capture. Again, this is not in depth. It's not meant to be in depth. It's just meant to introduce you to this type of tech. And of course, I'll summarize the whole week on Friday to make sure you guys know what you need to know. Okay. All right, guys. Later.